Okay, please go. So thank you so much. Apologies, and I tried to rush you through our presentation. Could you go to the next slide? So we'll tell you what Whisper, which is a speech foundational model, does with all the language and the different scripts doing transcription. And please, if you can't hear me, shout or write in the chat. So I will give you details and background about what Whisper is, and we'll give some examples of how scripts ended up being entangled with the Whisper transcriptions, and that is based on the kind of the working, the powerhouse of Whisper, which is its subtoken dictionary. And the scripts ended up being entangled because some subtokens are predicted by this system and they belong to different scripts. And I will present the two results of our experiment. So you can go to the next slide, please. So in a nutshell, Whisper is a speech foundational model led by self-supervision. What you can see on the left is the input. Whisper learns by seeing chunks of speech and their corresponding transcription. It's mostly trained on English, but it's also trained to do translation. So for each speech sound, like in Spanish, you may get the English transcription, and it's designed to do transcription, as a result of which you get the as input the sound of the WAV files and the corresponding transcriptions in the different scripts. I'm not going to talk you through the details, but you can see that goes in two parts. The left part, the blue part, is called the encoder, and our second experiment will extract the information available at the last layer of the encoder, the thing that says MLP, multi-layer perception. And we can move to the next slide. In a nutshell, what you need to remember is Whisper has a dictionary, a vocabulary. Some of it is designed to learn the task, like this is transcription, this is translation. Some of it is learned to use the timestamps. This is the beginning of the file, this is the end of the file. That's the green thing. And the most important aspect, it has text tokens corresponding to texts, not as word as we know it, but after the results of a process called subtokenization. I'm going to explain with the next slide. So for the record, there are different models. What you need to remember is whatever the models, there are two tokenization dictionaries, and we will mostly discuss the multilingual dictionary. Next slide, please. So this is a logarithmic scale representing all the languages used for the training of Whisper. And as you can see, it's unbalanced. See, remember, it's a logarithmic scale. Some languages have more than 400,000 hours of training data, that's English, and some languages have less than 1 hour of training data. And this results in inadequacy for some of the script mixes. Next slide. So byte pair encoding is a system I'm going to try to explain with the following slide. I need to skip time. So basically, this is a form of fusion, and I'll explain even better with the following slide that gives example. With subtokenization, you need to define a list of words. Could I have the next slide? And you define the size of the dictionary. So I'll spare you the algorithm. Let's go to the examples. So following one, just perfect. So here is a series of examples. The plan is to avoid meeting words that were never seen before. So to avoid this out of vocabulary word problems, engineers have come up with an idea. Let's represent words as subwords and define a size of the dictionary for the subword. And let's define a dictionary depending on the size of the dictionary, the reconstruction is different. So as you can see, for the same German word and English word, you could see that depending on the model, 50K means 50,000 words. That ends up with words being split into very small chunks. They're not morphological items, they're not morphemes, they're just sequences of letters. But you can realize that very frequent words like situation make it to the dictionary. So take-home message, the byte pair encoding algorithm favors the languages that are mostly represented, and they'll get up to have fully words, whereas languages that are rarer will end up being split into smaller sequences, and they're actually represented on a letter-based rather than on a word-based. More about this in the following slide. Some of the special tokens are used to represent timestamps, and I'll just explain that by describing the next slide. You can see that there are some specific special tokens, TT ranging from 0 to 1,500, and they literally corresponds to the chunk of 30 seconds that is used to represent speech. So these special tokens only represent duration. We may shift the following slide, skip it as well. Let's skip it. So that means, okay, so so that's the same idea. The duration is explained by the number after the TT special type token. And now let's move to the real thing. The following slide describes the consequence of what happens with a grapheme, the repository of graphemes, and whatever the model, the English model or the multilingual model, we have words that are complete, that are not split, and they correspond to 2/3 of the data, and so that's 65%, and words that are not words that are split are actually sequences of 1 or 2 letters, and they account for the third of the tokens. So that's the content of the dictionary of subtokens. Next slides give us the distribution of these subtokens. As you can see, for the English dictionary, it was based on GPT-2, and it was not actually processed, cleaned, as a result of which you have some tokens that do not make sense at all linguistically. They're the results of a lousy pre-processing. Another consequence for the English models of these tokenization issues in the following slide. You can see that some of the tokens are actually incomplete and not UTF-8 because they're the results of the byte pair encoding. We may shift to the other slide to inspect another consequence. That's the extraordinary number of characters that we have for words that do not correspond to expected words, and this does not correspond to any Zipfchen relation for the English lexicon. And if we shift to the next slide, we'll see that's the same, but not with a less severe with the multilingual model. There are indeed different subtokens of different sizes, but for the distribution in terms of number of characters, that is more plausible. If we shift to the next slide, we can see that the whole question is how is the mapping done between the acoustic realization and the subtoken mapping? And this is where the problem relies. In some cases, the mapping is done with subtokens that belong to alternate scripts of the language we want to transcribe. So We can move to the next slide. Case in point is the inability of the system to take into account the need for some languages to have specific initial, medial, or final representation of the script. And if we move again to the next slide, we can see that this question of multilingual models and how byte-pay encoding may affect them has already been investigated. So they looked at two specific types of features, literally parity, which corresponds to the number of subtokens that are required for the different words. And the other important concept is the concept of overlap, the fact that a single token may be used with other languages. Now we need examples, which this next slide will bring. So summarizing it, we want to know how many tokens are required to represent a text, that's fertility, and then we want to know what's the difference in the number of subtokens. Let's look at examples with slide 24. If we take the same sentence in different languages, you can see that English, being privileged in terms of training data, has a limited number of subtokens, and actually they correspond to words because they're very frequent. But if we take much rarer words such as Swahili or Azerbaijani, you can see that the words like divanda ended up being split into two words, or in the case of Swahili, a word like wangu ends up in being represented by three subtokens. So in terms of fertility, you can see that some languages are represented by many more subtokens than others. And this also is more likely to trigger errors in the transcription. And last, you can see that across languages, so far, in English and in Swahili, is the same token shared by the two languages. So there is overlap across the languages, overlaps in terms of letters, but more crucially, overlaps when the same sound will correspond to different scripts. And if we go to the next slide, we'll see that here, in the case of speech models, we're actually dealing with not a 2D problem, a two-dimensional problem, but a three-dimensional problems. We have parity and fertility issues. We have lexical overlaps issues, but we also have phonological overlaps, namely the same sound may have a corresponding subtoken belonging to different scripts in different languages, and this is where scripts end up being entangled. The same sound may actually be transcribed by a subtoken belonging to a different script. Let's move to the following slide. So in a nutshell, we have the same principle for all the languages. This is called the transcription task. We have WAV file as input, and we expect to have textual transcription as the output, but the output may be a mix of different languages. Cases in point on the following slide. For Vietnamese, you may end up with having Chinese scripts in the transcriptions. For the transcription of Punjabi, you may have Telugu used in the representation. And for the transcription of Urdu, you may see Korean typography. In the PhD by Benush, we've observed a certain number of characters belonging to different scripts for the transcriptions of Persian. So that's the core of the problem. How come we have this take-home message? Because of the subtokenization model and because of the imbalance of the different languages, so that some languages do not have the same type of representation. Most frequent languages in the training data ended up being chosen in the transcription. Let's move to the next slide. So in a nutshell, okay, so I've just explained that. We can move to the following slide. An important aspect of the byte pair encoding in that in some cases, some characters ended up being split over several bytes pair encoding tokens. Let's move to the next slide. Literally, the process will split some characters into two byte pair encoded tokens that are not necessarily letters as such. And if we move on to the next slide. Okay, again. So we use GlotScript to look at the wrongly assigned subtokens, and we did a second experiment. When we had one speech, we looked at the prediction, and not only the first prediction, the one that is given as output in the traditional commercial tool, but we looked at the corresponding probabilities of the 50 candidates. And if we look at the results on the following slide, we can see that for Persian, if we look at candidate 50, already 25% of the candidates belong actually to other scripts. This is a way of saying that Whisper works with associating acoustic signal with realizations. And if your script, your language is underrepresented in the training data, other languages might be suggested as candidates, therefore intermingling the different scripts of the different languages. Can we move to the next slide? Another case in point is the transcription of Persian, because Arabic is more present in the training data. In some cases, the letters for Arabic are actually used instead of Persian letters for the transcription. Let's move to the next slide. So this is basically the interaction of these two phenomena. On the left, the disproportion of the training data between the different languages in terms of sound, the dictionary of subtokens on the one hand, that end up in the entanglement of scripts. And our last slide is kind of a conclusion. We want to address the entanglement of scripts by having a form of entanglements between the disciplines. So we need linguists, we need computer scientists, and we need AI specialists to try to improve on the understanding of this so-called hallucination. How come a transcription of a language end up with having different mixed scripts in the transcription? And you can move to the last slide asking for questions. Sorry, I've been trying to keep on schedule.
Yeah, great. Thank you. Yeah. I think we can take 2 questions for Nicolas. Have any question? Yes. Do we have come up, please? Yeah, because we don't have a mic here. We have a mic here. Let me test this. Oh, it won't work. Okay, please come to ask question. Okay, come here.
Thank you for your talk. I had a quick question. So, if I'm understanding right, it seems that this hallucination of multiple writing systems is, for lack of a better way of saying it, an inevitable consequence of there not being any like prevention against that as a possibility. So, how successful have hard-coded attempts been to say there's a language recognizer that says, I recognize that the language that being spoken is Persian, and then only tokens associated with Persian script are used. Is that not a approach that is good in performance?
So as far as I'm aware, there have been two approaches that have been followed. One tries to associate a large language model as an output of the transcription and tries to correct the transcription, potentially paying attention to these entanglement of scripts. I suspect the second one would be a kind of a few shot prompting. Here are cases of mixed scripts. Now try to fix them. But as far as I know, for Whisper, they do code the language for the training phase. So there are tokens corresponding to the language identity. We know which language it is, but there is no systematic check in the decoder. So it's mostly what we're trying to work on now, what we call the division of labor between the encoder and the decoder. And the decoder assumes that the next token will tell you which is expected here. So incidentally, for languages like Arabic, which have citational forms of the letters and different forms in initial, medial, and final position, the encoder only includes the citational form, and the decoder knows whether it's initial or final form of the letter that needs to be installed there.
Okay. Thank you.
Last question. Yeah. It's not working.
Yes, I was just wondering, has the sampling rate gotten high enough so that you have absolute initial accuracy as far as listening to all of the details of the sound? Because I know 20 years ago, the sampling rate was lower than we had, Dragon, naturally speaking, etc. So is the sample rate so high now that it's not a problem as far as recognizing the initial audio input?
Yeah, they do have 24K sampling rates. So they do manage to have much better performance than was possible some 20 years ago.
Okay, thank you.
Yeah. Great. Thank you. Thank you, Nicolas.
Okay, thank you so much.